clears on countdown 1. This is the final go, no go for flight 2 of Starship. Again, our T0 is at 7 a.m. Central.
What happens to satellites when they're no longer useful? We can't shoot them down, so we've got to crash them somewhere, right? Programs, Trace here for D-News. Did you see that lunar eclipse a little while ago? Real pretty, right? What you probably didn't know was during the eclipse there was...
Welcome to the debate. Hello, we are back here with command figures. Right now, just a few hundred miles above our heads, there are millions of invisible millimeter-wide bullets circling the Earth at roughly 15,000 miles per hour.
Yeah, it's not exactly the peaceful, infinite expanse we think of when we look up at the night sky.
No, not at all. In low Earth orbit, or LEO, we are actually blindly rushing toward a terrifying tipping point. It's called the Kessler Syndrome.
Right, and for those who might only know that as a sci-fi buzzword, the Kessler Syndrome is a nightmare scenario. It was originally mapped out by NASA scientists Donald Kessler and Burton Corpellet back in 1978.
Basically, they realized that once a certain density of objects in orbit is reached, a single collision will create a massive chain reaction of exploding satellites.
Exactly. The high-speed shrapnel from that first crash destroys 2 more satellites, and then those destroy 4 more, and so on. It cascades.
It cascades until Earth is effectively trapped under this impenetrable cloud of high-speed shrapnel. And if we hit that tipping point, the consequences are absolute devastation for modern civilization.
Oh, instant devastation.
Right. Global GPS, commercial aviation, international banking networks, internet connectivity, all of it would be instantly destroyed, and it could remain entirely unusable for decades.
It is basically the ultimate bottleneck for modern human civilization. And today, our analysis is drawn directly from recent symposium papers, economic impact assessments, and technical models, things like the CASM stochastic simulation and the Naval Research Lab's Laredo detection project.
We have the data. The debate today is really about how we interpret the exact nature of this threat, and consequently, how we actually survive it.
Which brings us to the core question we are looking at today. Is the onset of the Kessler Syndrome fundamentally a slow-moving tragedy of the commons that we have to solve primarily through international regulation and population management?
Or is it an immediate volatile threat driven by sudden fragmentation events, one that requires urgent technological detection and resilience?
Exactly.
Well, I am going to argue that the Kessler Syndrome is at its heart a gradual systemic crisis. It's driven by the exponential launch of commercial mega-constellations. The math of orbital capacity is just incredibly clear.
But math doesn't account for random chaos.
It accounts for probability, though. And because of this predictable probability, the primary solution cannot just be some technological band-aid. It has to be strict regulatory population management. Specifically, we need to mandate the rapid deorbiting of derelict satellites within 5 years. Economic models show this is by far the most effective intervention to stop the cascading math.
And I take a very different view here. Viewing the Kessler Syndrome as a gradual, multi-century capacity problem, it ignores the catastrophic reality of sudden, violent shocks. Things like anti-satellite weapon tests and severe solar flares.
We can't predict those, though.
Which is exactly why I will be arguing that our absolute priority has to be technological defense. We need advanced collision avoidance and tracking systems for lethal, non-trackable debris right now. Geopolitical regulation is just simply too slow and too fragile to stop an imminent cascade. We have to survive the immediate environment first.
Okay, but if you look at the actual mechanics of the orbital debris crisis, it is the textbook definition of the tragedy of the commons. Space is a shared resource, much like our oceans or the atmosphere.
Sure, I agree with that.
Right, and uncoordinated commercial exploitation leads inevitably to depletion and pollution. Look at the KESM model. It's a stochastic simulation, meaning it runs thousands of probability scenarios on millions of objects in LEO.
Right.
It forecasts that under a business-as-usual scenario, LEO will become completely unusable in an average of 243 years.
Yeah, but 243 years is a massive average. It completely hides a lot of immediate danger.
It is a long time, but here's the critical part of that model. That timeline is accelerating at a staggering rate due to the deployment of commercial mega constellations. We are completely overwhelming the environment right now.
The numbers are definitely spiking, yeah?
Exactly. Companies are planning massive fleets. I mean, SpaceX alone is looking at up to 42,000 satellites for their Starlink network. To put that in perspective, the launch rate of payloads spiked from roughly 300 per year in 2018 to over 1,500 per year recently. The sheer volume of metal we are putting up there is fundamentally unsustainable.
I don't disagree that volume is increasing, but relying on a 200-plus year average accumulation model is dangerously complacent. The true existential threat doesn't come from a smooth curve of commercial growth.
You're talking about the unpredictable stuff?
Yes. It comes from sudden, highly volatile fragmentation events that instantly create lethal, non-trackable debris. We are talking about fragments between 0.1 millimeters and 3 centimeters. Ground radars simply cannot see them, yet they carry lethal kinetic energy.
But those are outliers.
Are they? Look at the recent Time Investigation's crash clock analysis. It models the space weather variable, specifically solar storms. If a Carrington-level solar storm, like the massive flare in 1859 that set telegraph wires on fire on Earth, hits us today, it expands our atmosphere and completely scrambles satellite avoidance maneuvers.
That is definitely a terrifying variable.
It is. The crash clock shows that if operators are blinded and unable to maneuver for just 24 hours, there is a 30% probability of triggering a Kessler cascade in a mere 2.8 days. Not 243 years, 2.8 days.
I see why you think that, but let me give you a different perspective. We have to trace the chronological timeline of this crisis to understand why the volume itself, and not just these random shocks, is the primary driver.
Okay, let's look at the timeline.
If we go back to Kessler and Corpele's foundational 1978 hypothesis, they mapped out a predictable mathematical growth of the threat. They noted that the Earth's atmosphere naturally cleans low Earth orbit. Atmospheric drag slowly pulls objects down until they burn up.
Which is true, mathematically.
Right, but Kessler realized that eventually the rate at adding new debris would outpace the rate at which atmospheric drag removes it. So fast forward to the modern era of mega constellations. Over the next 2 decades, the number of active satellites is expected to double.
So it's getting crowded.
Extremely. Think of low Earth orbit as a crowded highway. It honestly does not matter how good your brakes are or, how advanced your autonomous crash detection sensors are if the sheer volume of cars fundamentally exceeds the road's physical capacity.
But space is a lot bigger than a highway.
But orbits are specific lanes. If every single lane is packed bumper to bumper and there is no open asphalt to swerve into, a crash is mathematically inevitable. What we are facing is a predictable capacity issue. It's a systemic overcrowding, not just a vulnerability to a solar storm.
The highway analogy is neat, but it ignores the reality of how debris fields are actually generated in practice. When I look at the chronological timeline of space debris, I don't see a smooth curve of commercial traffic filling up lanes.
What do you see then?
I see massive, violent disruptions that instantly rewrite the risk profile of orbit for everyone. Let's look at the 3 major historical step increases in debris, none of which were caused by gradual commercial overcrowding.
Oh, you are talking about the military tests?
Exactly. First, look at the 2007 Chinese anti-satellite, or ASAT weapon test. They intentionally blew up their own defunct weather satellite. That single event added over 3,000 trackable fragments to LEO instantly, plus countless untrackable ones.
It was a massive mess.
And then, 2 years later, in 2009, you have the accidental collision between an active American Iridium satellite and a defunct Russian Cosmos satellite. Thousands more fragments. Then, in 2021, the Russian ASAT test destroyed Cosmos 1408, creating 1,500 trackable pieces and hundreds of thousands of untrackable fragments.
But those are isolated events.
These abrupt shocks completely invalidate the slow burn commercial capacity models. A single kinetic missile test can accomplish in one afternoon what takes decades of commercial launch accumulation. You can cap and regulate commercial satellites all you want, but you cannot regulate a kinetic missile test by a geopolitical adversary.
I fully acknowledge that those anti-satellite tests are devastating, but they do not occur in a vacuum. They occur within the broader context of orbit density.
The density definitely makes the fragments more dangerous, sure.
Right. A fragmentation event in 1980 was bad, but a fragmentation event today, in a highly congested orbit, is what actually risks the cascade. And I want to pivot to the terrestrial consequences of that density reaching a breaking point. Because we will hit what is termed an economic Kessler Syndrome long before the sky goes dark with physical debris.
Meaning the cost of operating in space becomes too high?
Exactly. LEO becomes economically unusable. The international economic model suggests that a severe Kessler event could inflict $191 billion in immediate terrestrial losses. Plus, it would create a 2% drag on global GDP.
The financial hit would be catastrophic.
We don't just use space for research anymore. Our global infrastructure is completely dependent on it. Take offshore oil drilling platforms. They operate far beyond ground-based networks. Without satellite communications, it is estimated they would lose nearly 90 million euros almost immediately because they simply cannot coordinate logistics or safety protocols.
Those numbers are staggering, but
Let me give you an even more granular example. Think about remote ATMs and point-of-sale terminals. You know those little card readers you use at a rural gas station or a local grocery store? People assume those run purely on internet cables, but they rely entirely on GPS timing signals.
oh, right, for the atomic clocks.
Yes, the satellites act as highly precise atomic clocks, allowing the cryptographic handshakes between banks to synchronize and verify transactions. If the GPS constellation goes down, those terminals completely fail. Physical transactions stop.
It's a huge vulnerability.
The core of my argument is that the soaring costs of insurance, of replacing hardware, and of constantly maneuvering around debris will bankrupt the space industry. That economic threshold will break us before a physical wall of debris blocks our access to the stars.
I'm sorry, but I just don't buy that. Let me tell you why. Economics are entirely downstream of physics. You are worried about insurance premiums and banking handshakes, but the physical reality of untrackable debris is a far more pressing, immediate threat.
I mean, if the economics fail, the satellites fail.
But you can't insure a satellite against something you can't even see coming. Let's talk about the brute physical realities of what we call lethal, non-trackable debris.
Which, just to clarify for the listener, is anything smaller than what ground-based radar can reliably track. So typically under 10 centimeters.
Right, and the danger zone is really those fragments between 1 millimeter and 3 centimeters. Let's take an aluminum sphere that is just 1.2 centimeters in diameter, essentially the side of a glass marble.
Okay, a marble.
If that marble is traveling at orbital velocities, striking a spacecraft's surface at 6.8 kilometers per second, it releases 56,500 joules of energy. For context, the European Space Agency did an impact test showing that a projectile of that exact size, traveling at that speed, will catastrophically blow an 18-centimeter thick crater into a solid block of aluminum.
Wow. Just from a marble.
Now imagine that hitting a delicate satellite bus or a fuel tank. These fragments are out there by the millions, and ground radar is completely blind to them. Economic models are totally secondary to the immediate need to survive that kinetic environment.
Okay, I have to push back here. You are talking about dodging fragments that are 1 millimeter wide, traveling at 15,000 miles per hour. You just admitted ground radar literally cannot see them.
Ground radar can't know.
So how on earth is a satellite supposed to dodge a bullet it can't even perceive? You are advocating for technological defense, but you are describing an invisible threat.
That is exactly why the Loreto project is so vital. It is a brilliant piece of engineering funded by NASA to solve precisely this blind spot. Because ground radar can't see these millimeter-sized bullets, Loreto moves the detection system up into orbit, onto the spacecraft itself. It creates what is called a virtual light sheet.
A light sheet? Like a laser?
Exactly. The satellite projects a thin sheet of laser light out into space in front of it. It's like turning on your headlights in a snowstorm. When a tiny piece of microdebris passes through that light, it scatters photons.
Okay, but at those speeds, isn't it too fast to catch?
To detect that incredibly brief flash of scattered light, they cannot use a regular digital camera. A traditional camera would be too slow. Instead, they use a neuromorphic camera.
Ah, I know a bit about this. A neuromorphic camera operates differently than a standard digital camera, right? It mimics the human eye rather than just snapping pictures.
That's a great way to put it. A traditional camera uses a shutter to take discrete frames, like 30 or 60 frames per second. But when you are dealing with hypervelocity objects moving at thousands of meters per second, a frame-based camera leaves gaps in time.
Right, blind spots between the frames.
Exactly. The marble could pass through the light sheet during the microsecond the shutter is closed, and you would never know it was there until your satellite exploded. A neuromorphic camera doesn't have frames. There is no shutter. Each individual pixel on the sensor operates entirely independently and asynchronously.
So the pixels are just, waiting in the dark?
Yes. A pixel only fires and records data if the brightness it specifically sees changes above or below a certain threshold. It records these changes in microseconds. This continuous, unbroken stream of data allows the satellite's computer to detect high-speed, sub-millimeter shrapnel that currently goes entirely unseen.
It is a very clever workaround.
If we don't deploy this hardware up there to map, track, and eventually automate dodging these lethal fragments, your economic models won't matter because the commercial fleets will literally be ripped to shreds by invisible shrapnel.
The technology behind neuromorphic sensors is undeniably fascinating, and I don't doubt it works in a vacuum. But let's look at the actual efficacy of these different mitigation strategies objectively, on a macro level.
Okay, let's look at the numbers.
The Kessler model didn't just project the disaster. It actually ran an economic evaluation of various solutions to the debris crisis, scoring them on a benefit-to-cost ratio. Do you know what scored the highest by a massive margin?
Population management.
You mean the 5-year deorbit rule?
Exactly.
This is a regulatory mandate that would require commercial operators and governments to deorbit their derelict satellites within 5 years of the end of their operational lifespan. That's drastically down from the current, very loose standard of 25 years.
Right, getting the dead weight out of the sky faster.
And this approach yielded an overwhelming benefit-to-cost ratio of 7.1. Let's compare that to technological defenses. Spacecraft hardening, putting more armor and shielding on satellites, only scored a 2.1. And a launch moratorium, which would just be stopping all rocket launches entirely, was practically useless at 0.1.
Wait, why is a moratorium useless?
Because the debris already up there will continue to collide with the dead mass we've left behind. Which brings me to the core logic of population management. The reason a 5-year deorbit rule is mathematically superior to just adding thicker armor or fancy detection lasers is because dead mass acts as a fragmentation multiplier.
A bullet sponge.
Exactly. If a 1-centimeter marble hits an 8-ton dead satellite from the 1990s, it doesn't just punch a hole, it shatters the structure into 10,000 new bullets. Taking the massive targets out of the sky is exponentially cheaper and more effective than trying to build an impenetrable shield for every new satellite.
I see the logic there.
How can technological band-aids solve what is fundamentally a systemic overcrowding problem? The math says we have to remove the massive derelict objects that act as bullet sponges.
That's a compelling argument, but have you considered the fatal flaw in population management? It requires global geopolitical compliance. And as the anti-satellite tests from China and Russia explicitly prove, that compliance does not exist.
We can build international treaties, though.
We do not have a global space police force to ensure a rogue operator or a competing military power deorbits their defunct spy satellite. Population management is a beautiful mathematical ideal on a spreadsheet, but in the real messy world of geopolitics, we have to rely on technologies that are entirely within our own control.
But relying on individual evasion just creates a different kind of chaos.
Not if the evasion is autonomous and coordinated. Look, collision avoidance still has a highly effective benefit-to-cost ratio of 4.0 in the Kessler model. We need advanced tracking combined with active evasion technologies like atmospheric braking sails that can pull a satellite out of the way.
I mean, even Kesem suggests combining approaches.
Right. I will freely acknowledge that the Kessler model shows an all-of-the-above mitigation approach combining regulation and technology yields the highest combined ratio of 7.9. But I absolutely insist that without autonomous onboard technological defenses to detect and dodge the untrackable debris, your regulatory management will fail. It fails the moment a bad actor decides to ignore the rules or the moment a solar storm hits.
I want to focus on that evasion aspect. Relying purely on evasion assumes there will always be a safe trajectory to move into. Returning to our earlier analogy, if the highway is completely blocked, steering just causes a different collision.
But with a light sheet, you map the safe zones.
Sure, when a piece of lethal, non-trackable debris comes hurtling toward an active, maneuverable satellite equipped with Lorado, maybe it dodges. But what happens when that fragment is heading toward one of those massive spent rocket bodies? You cannot put a neuromorphic camera on a dead rocket booster.
No, you can't.
Therefore, unless we have strict international regulations forcing operators to clean up their dead mass, the background environment becomes so highly charged with shrapnel that even your advanced cameras will be overwhelmed. A satellite can only dodge so many times before it runs out of fuel.
You are assuming that cleaning up the dead mass is enough to stop the cascade. But what if the cascade trigger isn't a dead satellite getting hit? What if the trigger is the environment itself changing overnight?
Is space weather variable again?
Exactly. We haven't fully unpacked that. Let's go back to the CRSC crack analysis and the Carrington event. If a massive coronal mass ejection hits Earth, it dumps enormous amounts of energy into the upper atmosphere. The atmosphere swells outward. Suddenly, the aerodynamic drag on every single object in low Earth orbit changes unpredictably.
Meaning our tracking catalogs on Earth become instantly inaccurate.
Completely obsolete in a matter of hours. And at the exact same time the atmosphere is swelling, the geomagnetic storm scrambles the electronic systems used for ground communication. So you have a situation where satellites are drifting into new, unpredictable orbits and ground control cannot send them commands to move.
That is a nightmare scenario.
If an operator loses the ability to send a maneuver command for just 24 hours, the probability of a Kessler cascade jumps to 30%. In a scenario like that, the only thing that saves a multi-billion-dollar mega constellation is onboard autonomous defense.
Without waiting for ground control?
Right. The satellite has to sense the incoming threat with a neuromorphic camera and fire its thrusters without waiting for a human on Earth to give the green light. You can write all the 5-year deorbit regulations you want, but a solar storm doesn't respect United Nations treaties.
I concede that a severe solar storm represents a massive, unpredictable vulnerability. However, the solution you're proposing, building autonomous evasion systems for tens of thousands of satellites, simply increases the cost and complexity of every single unit launched.
Survival usually does cost more.
But that drives us faster toward the economic Kessler Syndrome. Think about the barrier to entry. If every commercial operator has to outfit their fleet with military-grade neuromorphic detection lasers and autonomous AI thrusters just to survive a week in orbit, space becomes the exclusive playground of superpowers.
It's already an expensive industry.
But developing nations are already being excluded from the space economy because of these rising costs. Major powers can absorb the risk and expense of Lorado systems, but smaller nations will be forced into permanent dependency on imported orbital services. By focusing on international regulations capping the number of objects, enforcing strict deorbit protocols, we keep the environment safe enough and cheap enough that standard commercial operations remain viable for everyone.
I hear your concern about cost, but historically, technology scales and becomes cheaper over time. The first, neuromorphic sensors are expensive, absolutely. But once the hardware is standardized and mass-produced by commercial entities, it becomes just another off-the-shelf component, like a star tracker or a solar panel.
It takes time to scale, though.
On the flip side, the cost of losing LEO entirely is unquantifiable. The loss of Earth observation satellites that monitor severe weather and hurricanes, the loss of logistics tracking for global shipping networks. These aren't just inconveniences, they are matters of life and death.
I don't disagree with the stakes.
The 243-year Kesem average gives us a false sense of security because the standard deviation on these models is wild.
There is a non-zero chance of the syndrome initiating within our lifetimes. We simply cannot risk the future of global connectivity on the naive hope that competing superpowers will suddenly decide to perfectly manage a shared commons.
Well, I think we have clearly defined the boundaries of this problem and the tension between our two approaches. To summarize my position, the Kessler Syndrome is, without a doubt, a macro-level resource management crisis.
The tragedy of the commons.
Yes, the math of the commons is inescapable. Without strict, binding international population management to curb the geometric growth of mega-constellations and legally force the removal of dead mass, the tragedy of the commons in low Earth orbit will inevitably lead to an economic and physical collapse. Technological workarounds, no matter how brilliant, simply cannot outpace the mathematical reality of exponential overcrowding.
And to summarize my view, while the underlying math of the commons is indeed real, the actual trigger for the Kessler Syndrome will not be a slow 200-year degradation that we can gently regulate our way out of.
It's the unpredictable shock.
Test or a massive solar flare blinding our ground control systems. Therefore, investing heavily in dynamic, autonomous technologies like Lorado's neuromorphic detection and automated collision avoidance is our only realistic survival strategy in what is fundamentally an unregulated, volatile orbital environment.
Despite our different approaches to the solution, I believe we share critical common ground today. We both agree that mankind's productive use of low Earth orbit is hovering on a knife's edge.
Absolutely. We are playing a dangerous game.
Losing this orbital environment would systematically dismantle the modern digital and logistical world as we know it, from the ATMs in our rural towns to the GPS networks routing our flights. To the listeners, there is so much more to this issue than we could cover today, and the mechanisms behind these events are deeply fascinating.
There is some incredible research out there on this.
I highly suggest you look deeper into the Kessler stochastic model and the incredible engineering behind the Lorado project to truly understand the scale of this challenge. The night sky might look peaceful, but the invisible highway above us is rushing toward a breaking point.
Thank you for listening. Do not forget to click like and subscribe and write your opinion in the comment section.